This is going to be a video on the first part of Chapter 9, which is on solutions. All right, when we talk about a solution, we want to talk about the two pieces that are in our solution, and that is the solute and the solvent. So in this case, I have a solution, which remember is just a homogeneous mixture. That means that you can't tell the difference between the two. And so I have salt dissolving in water. So the solute is the substance that I have the lesser amount of, and that's the amount that's being dissolved in the solvent. So in this case, the salt is my solute, and my water is my solvent. Now the solute is spread evenly throughout the whole solution, and I can't see the individual particles because they're dissolved. Now those solutes and solvents can be in different phases. They could be solids, liquids, or gases. So for example, if we have air, that means I have a gas solute in a gas solvent. So my solution is in the gas phase. But I could also have gases in liquids. For example, if I'm going to have pop. So in that case, I have carbon dioxide dissolved in the water. I could also have solids in liquids, just like we talked about with the salt water. That would be like seawater, where I have salt dissolved in water. I could also have solid in solids. In that case, I could have something like brass, which is an alloy, and that is zinc and copper mixed together. So typically we think about solids in liquids, but that doesn't necessarily have to be the case. So in this case, we want to identify which is the solute and which is the solvent. So I have 2 grams of sugar and 100 milliliters of water. So in that case, the sugar is the less amount, so the sugar would be the solute. In case number 2, I have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. So in this case, I have the lesser amount, so that would be my solute. You go ahead and look at number 3 and number 4. Pause the video if you need to, and then decide what you think is the solute. All right, so in number 3, I have 50 milliliters of water and 1.5 grams of sodium chloride, so sodium chloride has to be my solute. And for air, I have 200 milliliters of oxygen and 800 milliliters of nitrogen, so the oxygen is the one in the smaller amount, so that would be my solute. Water is the most common solvent that I have. It is a polar molecule, and that means it also forms hydrogen bonding. And water is the most common solvent because it's fairly abundant. It dissolves lots of other polar substances, and it's non-toxic and fairly inexpensive. Now, in the human body, we are pretty much 60% by water. If I have as little as 10% of my body fluid lost, then I suffer from dehydration. And water can be lost or replaced by liquids and foods that are in our diet. If we want to look about what equation looks like, if I have a solid, sodium chloride, and I'm dissolving it in water, then it breaks apart and it forms ions. So I have sodium ion and the chloride ion. And when I have things that dissolve, there is going to be an attraction between the solute and the solvent. So polar things like water dissolve other polar solutes, such as sugar and or ionic solutes. Now nonpolar dissolve nonpolar. And this idea of polar dissolving in polar, nonpolar dissolving in nonpolar is the phrase likes dissolve likes, meaning polar dissolve polar, nonpolar dissolve nonpolar. And polar and nonpolar are not alike, so they will not form a solution. In this case, I can see I have water and something that is nonpolar, so they don't mix. Here I have iodine, which is nonpolar, and I have water, which is polar, so those don't mix. And in this case, I have one thing that's polar and one that's nonpolar, and they're not mixing. So in order for them to dissolve, they have to be the same. So it wants to know which of the following will dissolve in water, why or why not. So sodium sulfate, I can see sulfate, and sulfate is one of our polyatomic ions, which means, and this is a metal, so this is ionic. And if it's ionic, that means it will dissolve in water, because ionic things will dissolve in water just like polar things can. Now the next one, I have gasoline, which is nonpolar. Nonpolar will not dissolve in water because nonpolar and polar do not mix. Iodine, just like that, that would be nonpolar because the difference in the electronegativities would be 0. So nonpolar will not dissolve in water. And lastly, I have HCl, and HCl, in this case, the difference in electronegativity is greater than that 0.4, and we would have a dipole that's pointing toward the chlorine, so this would be polar, and since it's polar, it will also dissolve in water. We also have electrolytes. Now electrolytes are substances that are going to separate into ions, and they're going to conduct electricity. Now if they form a lot of ions, then it's going to be a strong electrolyte. If they form very few ions, then if they're a weak electrolyte. And if they don't form any ions, they're a non-electrolyte. And this is a conductivity tester. This is a way that we can figure out if they're going to dissolve in water. And we would have seen this before when we had our lab and we were looking at ionic compounds and covalent compounds. So if it lights up bright, it's a strong electrolyte. If it lights up dim, it's a weak electrolyte. And if it doesn't light up, then it's a non-electrolyte. And when we look at these in chemistry, if they have a single arrow that's going over and they're forming ions, then that means this is going to be a strong electrolyte. It's going to break up completely into ions, and it's going to make an aqueous solution. Aqueous meaning dissolved in water. All right, so we have to figure out, complete each of the following for strong electrolytes. So CaCl2 plus solid, so if it's a strong electrolyte, it's completely going to dissolve in solution into ions. So here I have calcium plus 2, and I have 2 chlorine minus 1, and they're both aqueous. In the second case, I'm going to have 3 potassiums, and I'm going to have 1 phosphate. So I look for 3 potassiums and 1 phosphate where they are both aqueous. Now, if they're weak electrolytes, they only form a few ions. So now we're going to show this with a double arrow. Last time for strong electrolytes, we just had 1 arrow going like that. For a weak electrolyte, we're going to see 2 arrows showing that it's reversible. So it forms a few ions, but those few ions also go back and result in things not being dissolved. Now, things that are non-electrolytes, nothing happens. So they don't produce ions in solution, and they don't usually conduct electrical currents. All right, so strong electrolytes, they break up completely and form ions, and they will conduct electricity. And things that are ionic are going to be strong electrolytes. Weak electrolytes kind of dissolve. They make a few ions and they conduct weakly, meaning that light bulb isn't going to be very bright. And most of these are going to be acids or bases. These are going to be weak acids or weak bases. Non-electrolytes are not going to form any ions, and therefore they're not going to conduct. And these are going to be molecular compounds, meaning covalent bonds. Now, when we talk about equivalence, we talk about the amount that's equal to 1 mole of charge. So if I have 1 mole of sodium and it has a +1 charge, it has 1 equivalent. If I have 1 mole of calcium and it has a +2 charge, then I have 2 equivalents. So basically, the equivalent is telling me what is the charge if I have a mole of that substance. So here's some different ions. And you can see a +1, +2, +3. This is a -1. This is a -2. The sign doesn't matter. The equivalents are just what that number is. So 1, 2, 3, 1, 2, that's the number of equivalents. So whether it's a positive or negative charge is irrelevant. The equivalence is just how many charges. Now electrolytes, we talked about things that conduct electricity. You basically are a giant walking electrolyte. You have sodium ions dissolved in the water that's in your body. You have potassium ions and you have bicarbonate ions. And all of those electrolytes are going to form certain functions in your body. So the sodium ions help to regulate water content. They also are going to carry electrical impulses through the nervous system. That's because they are electrolytes. Potassium ions are involved in the transmission of electrical impulses, and they help to maintain regular heartbeats. And as far as maintaining the pH in your blood, that's where bicarbonate ions come into play. These are just some different ions that you're going to have in your body, and that's telling me the concentration of those. All right, so back to equivalents. If I have 1 mole of Fe plus 3, how many equivalents are there? Well, that's the charge, so there has to be 3. Now in this case, if I have 1 mole, I have 2 equivalents, but I have 2.5 moles. So 2.5 moles times 2 equivalents for each mole is going to tell me that I have 5 equivalents. Now in this case, I have an intravenous bottle, contains sodium chloride. If the sodium iodine produces 34 milliequivalents per liter, how much does the chloride ion produce? Well, I have 1 sodium and 1 chlorine. They both have a charge of plus, and this one's minus, so they both have a charge of 1. So if sodium is 34, then the chlorine also has to be 34. Solubility is one way that I can classify a solution, and solubility is telling me the amount of solute that dissolves in a specific amount of solvent at a given temperature. It's going to be affected by the type of solvent and by the temperature. That's why we always designate the temperature. And it's going to be expressed as grams of the solute per 100 grams of my solvent, which is generally water. If my solution is unsaturated, then that means it contains less than the maximum amount. And that maximum amount is called your solubility that we just looked at. So if it's unsaturated, it contains less than the saturated amount, which is the solubility. It means it can still hold more. If it's a saturated solution, that means it can't hold any more solute. It's got the maximum amount in there. And if it's saturated, that means it is at the solubility. So if your solubility is, let's say, 4 grams in 100 grams of water, and you're adding 4 grams, then you are saturated. If you're going to put in only 2 grams, then it would be unsaturated. Okay, so at 40 degrees, the solubility of KBr is 80 grams in 100 grams of water. That's my solubility. I have to decide if these are saturated or unsaturated. So if I have 200 grams in 200 grams of water, I need to know how much would be in 100 grams. So if 200 grams dissolve in 200 grams, that means I have 100 grams dissolving in 100 grams of water. My solubility is 80. So in this case, I am adding more than my solubility. So this has to be saturated. Now in this case, I have 25 grams in 50 grams of water. So 25 in 50 grams of water. So in 100 grams of water, that'd be times 2, so that would be 50 grams. 80 is telling me how much will dissolve. I'm trying to dissolve less than 80, so this is going to be unsaturated. A lot of ways that we can look at that is looking at a solubility graph like this. So this is going to be telling me my solubilities. So if I want to look at, let's say, glucose at 20 degrees, there's glucose at 20 degrees, looks like I could dissolve maybe 78 grams. So 78 grams would dissolve in 100 grams of water. And that tells me that is my solubility. So I can read my solubility at various temperatures. I can see that for glucose, that curve goes up, which means as the temperature increases, I can dissolve more and more. So for solid solutions, that solubility is going to increase as my temperature increases. However, if I have a gas solution, that means I will only dissolve less as the temperature increases. So those are opposites. So for solids in liquids, the solubility increases along with temperature. But for a gas, it's opposite. What that means is, for example, when you pop, if the temperature gets warmer, that means less carbon dioxide will actually dissolve in there, and it'll be flatter. So you want to serve it when it's cold, because if you have a low temperature, you're going to have more solubility. Whereas for things that are solids and liquids, like hot cocoa or tea, you want to have them warm, and you would dissolve more. Henry's law states that the solubility of a gas is directly related to the pressure. And if I have higher pressures, then I can dissolve more, which in a can of pop, I can dissolve a lot in there when it's under pressure. But when I open the lid, there's less pressure, so that means the solubility decreases. So why could a bottle of carbonated drink possibly burst or explode when it's left out in the sun? Well, if the temperature is warmer, then that means I'm going to have more pressure. And if there's more pressure, it's going to be too much for the can, and it's going to burst. Why do fish die in water that's too warm? Well, if it's too warm, then that means for gases, so now we're looking at gases like oxygen dissolved in the water. If it's too warm, there's not enough oxygen dissolved in the water, and the fish need the oxygen, so they're going to die. Let's go back to Okay, so our equation says that pressure is proportional to the solubility, or the concentration. So S tells me my solubility, P tells me my pressure, and K is a constant. And that's the equation that a lot of times we use for Henry's law. Ionic compounds. Ionic compounds dissolve in water because ionic compounds will dissolve in water, and if they dissolve, they're called soluble salts. So ionic compounds are salts. If they don't dissolve in water, then they are insoluble salts. So any ionic compound is a salt, and if they dissolve in water, they're soluble. If they don't, they're called insoluble. We have to look at our solubility rules to decide if it's going to be soluble or not. So if I have lithium, sodium, potassium, ammonium, nitrates, or acetates, those are all soluble. And there are no exceptions. Chlorine, bromine, and iodine are soluble unless I have silver, lead, or mercury with it. So if I had silver chloride, that's not soluble. It would be insoluble. Sulfates are soluble unless it is with one of these other compounds. So if I had calcium sulfate, that would be insoluble. Otherwise, if I had lithium sulfate, that would be soluble because all lithium compounds are soluble. So if it is one of these ions, that's going to tell me it's soluble. If it's not, it's going to be insoluble. So I have to use the solubility rules to determine if each one is soluble or insoluble. Well, our first rule said that sodium compounds are soluble. So this is going to be soluble. Next one, I have magnesium carbonate. So I have to look for my carbonates. Oh, they're not on here. So if carbonates aren't on here, that must means that it's not soluble. So this is going to be insoluble. I have lead chloride, so I have to find out about chlorides. Chlorides are soluble, but not with lead. So this is going to be insoluble. Insoluble. Magnesium chlorides. Well, we just said chlorides were soluble unless it was with silver, mercury, or lead. So that means this one is going to be soluble. I can use my solubility rules to help me decide. So if I mix two things together, I can decide, this is going to be a double replacement reaction where silver and sodium are going to change places. I have to decide if a precipitate's going to form. So here I have sodium nitrate, and according to my solubility rules, anything with sodium is soluble, and nitrates are also soluble. So if it's soluble, it dissolves in water, and it forms aqueous solution. Now silver chloride, chlorides are soluble, but not with silver, mercury, or lead, which means this is not soluble. So this is going to make a solid, which is going to be a precipitate. First of all, I'm going to have to write my complete equation. So my full equation, in this example, I have lead nitrate and sodium chloride. So the lead and the sodium are going to switch places. So sodium's going to go over here and go with nitrate. So sodium goes with nitrate. And this is a +1 and this is a -1. So it's just 1 to 1. Here I have the lead going with the chloride. Lead is a 2+ and chlorine's a -. So they're going to have to crisscross. So I have PbCl2. Now nitrates are soluble, so that one's aqueous. Chlorides are soluble unless it's with silver, mercury, or lead. So that means this is not soluble, so it's a precipitate. It's a solid. Now my ionic equation is going to break all these apart into ions, because all these are ionic compounds, and we know that when they dissolve in water, they break apart into ions. So I would have lead ion, and I have 2 nitrates. My 2 is missing here, so 2 nitrates. I have 2 sodiums, and I have 2 chlorides. This one does not split apart because it doesn't dissolve, therefore it can't form ions, so it stays together. I have 2 sodiums and 2 nitrates. So that's my total ionic equation. Everything's separated into ions. Now the things that are the same on both sides, like my nitrates and my sodiums, those are called spectator ions. And my spectator ions will cancel out because they don't do anything, they just watch. And my net ionic equation is what's left. So the lead and the 2 chlorides making lead chloride. That's how we're going to write total ionic and net ionic equations. Before, when we looked at solutions and we were categorizing them, we talked about them being saturated, unsaturated solutions. Well, that's kind of vague. So we want to be able to actually calculate concentrations of solutions. So in order to calculate the concentration, we take the solute on the top and the solution on the bottom. And we can look at mass percent, volume percent, mass by volume percent, or molarity. All of those 4 are going to be ones that we're going to look at. So if it's mass percent, then typically it looks like percent m by m, meaning percent mass by mass. And that's going to tell me the mass of the solute in the mass of the solution. And the solution is the solute and the solvent together. So since it's mass, it's going to be in grams. And to make it a percent, I take it times 100. So my mass percent is mass of the solute over mass of the whole solution times 100. Well, if I have a solution and I'm going to put 8 grams of my solute in 42 grams of water, then I would have 8 grams is my solute. My solution would be 8 plus 42, which is 50 grams of the solution. And then take it times 100, and I have 3 significant figures, so my percent is 16% by mass. I can also look at volume percent. It's the same thing, except instead of grams and masses, I'm going to be using volumes. So volume of the solute over volume of the solution. So if I have 7 milliliters of solute in 100 milliliters of the solution, 7 over 100 is going to tell me my percent, which would be 7%. Now mass by volume percent is pretty much the same thing, except we want mass on the top, grams. We want volume on the bottom, which is our milliliters. So if I have 5 grams of solute, 5 would go on the top, 100 milliliters of solution would go on the bottom. Take it times 100 and I get 5%. Molarity is the one that's different because it's not a percent. Molarity is how many moles of solute I have if I have a liter of solution. So if I have 2 moles of sodium chloride and it's dissolved in water to make 1 liter solution, I would take 2 moles divided by my 1 liter, and I find out that 2 divided by 1 is 2, so I have a 2 molar solution. So this capital M means molar, which is molarity, and I pronounce it just molar, the first part of molarity. And here they're showing us if I wanted to make a solution, I would put in my 2 moles of sodium chloride. I would use a volumetric flask and I'd fill it up with distilled water up to the line on the neck, and that would tell me that I have exactly 1 liter. So that would be my 2 molar solution.